Hi, I'm James. In the next 5 minutes I'll show how I built a model to predict the hourly electrical output of a combined cycle power plant from 4 ambient sensors. It predicts to within about 3 megawatts. I'll cover 4 things: the approach and metric, the features and algorithms, the validation strategy, and the comparison and evaluation. 4 decisions made strictly in this order. What kind of problem is this and how do I score it? What goes in, and what could fit it? How do I split the data so the score is honest? Then compare, select, evaluate. The discipline throughout. The test set stayed sealed until the last step. First, the approach. Every row carries its actual measured output, so the data is labeled. That makes it supervised. And output is continuous, 420 to 496 megawatts, not a category, so regression. For the metric I chose root mean squared error, in megawatts. 2 reasons. It's in the same units as the target, so the number means something to a plant operator. And squaring the errors punishes large misses harder, which matches the business reality, where one badly wrong forecast costs more than several small ones. Second, what goes in? All 4 sensors earn their place. Temperature dominates, at -0.95 correlation. Hot air is less dense, so less mass flows through the turbine and output falls. Vacuum is second but heavily correlated with temperature. Pressure and humidity are weak yet independent. I also engineered squared and interaction terms, because output bends at the temperature extremes. For algorithms I lined up 6 families, from linear regression as the interpretable baseline, up through k-nearest neighbors, support vector regression, random forests and gradient boosting. Third, the split. I shuffled all 9,568 rows and held out 20%, 1,914 rows. As a test set I did not reopen until the end. The remaining 7,654 became the training pool, each row tagged with a fold from 1 to 5. I chose 5-fold cross-validation over a single fixed validation set, and the data justifies it. My fold RMSEs ranged from 4.39 to 4.68. Draw fold 1 alone and you'd report a number 0.2 megawatts optimistic, the same size as the gap between competing models. Fourth, the comparison. 14 candidates, all through those same 5 folds, different feature sets, different hyperparameters, different algorithms. Linear on 2 features is worst, at 4.97. All 4 features gets to 4.58, engineered terms 4.35, polynomials 4.20. Then a real jump. The tree ensembles land between 3.30 and 3.50. Gradient boosting wins at 3.30. One caveat. That win is real. The margin beats its fold-to-fold standard deviation. But ranks 2, 3 and 4 sit within 0.04 of each other, and that gap is noise. Choosing among them on cross-validation alone would be overfitting the validation set. Here's the final model. On the left, all 1,914 held out hours plotted predicted against actual. The dashed line is perfect prediction, and the points hug it right across the operating range. On the right, the live Excel workbook, scoring those predictions with formulas. RMSE 2.98 megawatts. May 2.19. R squared 0.969. So how does it perform on my metric? Context first. 2.98 beats the naive baseline by 82%, and a well-specified linear model by 33%. That's what justifies the complexity. Is it honest? Test RMSE came in below the cross-validation estimate, expected, since the final model trains on more rows than any fold did. And the test set played no part in selection. Operationally, 92% of forecasts land within 5 megawatts. The residuals tell the more interesting story. The model is unbiased, but heavy-tailed. The RMSE to May ratio is 1.36, meaning most predictions are excellent and a few are badly wrong. The worst overshoots by 27 megawatts. Those hours are plant-side events that 4 ambient sensors cannot see. Which is exactly why RMSE was right. It surfaces those misses, where May would have averaged them away. To close, Supervised regression, because the data is labeled and the target continuous. RMSE in megawatts, because it's interpretable and punishes the misses that cost money. 80-20 holdout plus 5-fold cross-validation, test set opened once. And a gradient boosting model accurate to 2.98 megawatts. The honest limit, closing the remaining gap needs new information, not more tuning on the same 4 columns. Thank you.